All right, everyone. Well, welcome. I am JJ. Let's go ahead and tackle an example problem. So in this one, we have a rigid crank arm, this thing that goes at an angle here. It's loaded and support is shown. Let's determine our support reactions. So what are our support reactions? Well, I have a pin here at A. Let's go ahead and label that. That's a pin at A. And up here, pin at A. And then I have a thin link or a two-force member. We'll call that BC. Thin link BC. Thin link BC. Again, we should be able to look up in our tables and see, what do I do with a pin? What do I do with a thin link? We need that to be able to draw our free body diagram. Let's go ahead and start trying to set up that free body diagram. That should be my first step. Anytime I'm using an equilibrium equation, I have to have a free body diagram that goes along and ties in with that. So we are applying equilibrium to solve this out, make a free body diagram. Don't skip that step. If I were doing this, I'd say let's circle around our object. We're going to try to cut through our supports. It'll help us envision what do we need to include in here. So I know I'm going to come down and cut through the pin at A. I'll go around the rest of the crank arm in here. As I come back up, though, I'm just going to get sliced through the middle of that thin link and then come down and close out our circle. My supports I cut through as I try to free this from the supports, whatever's holding it to the ground or to the wall, need to show up as unknowns in my free body diagram. That circle step helps us visualize that out. I tell my students as they're learning free body diagrams to come in and practice drawing that circle. It will help them do it correctly. When they come to my office and they're struggling with a problem and their free body diagram's wrong, I will make them re-circle everything. So we get used to those, probably a step we can skip over. For now, let's go ahead and practice that. So we circle around everything. Then we can come in and draw our free body diagram. F, B, D. It's going to be our next step in our work in here. So just down below, I can get the general outline of this. It's just something shaped like this. I don't need to include that thickness in there. If no thickness is given, I would assume it's infinitely thin. So just something like this. We can take that and come in then and start trying to figure out, what do I need to include in here? So let's just start at A. I have a pin here at A. I should know anytime I have a pin, I want to work with an X component and a Y component. So I'm just going to guess directions at this point. I'm going to guess that AY is going straight up. And pick a name that makes sense. This is only in the Y direction. It's at A, so I'm calling it AY. Don't call, if you ever have a force at an angle, don't call that AY. Only do this if it's in the Y direction. But let's guess the AX. I'm going to assume it goes to the left. AX. Again, these are just guesses right now. When we actually apply equilibrium, the math will tell us if we're right or wrong. We'll present our answer in a way that, like, realistically says, what's my magnitude? And I'll give the correct direction on it for any support reaction. So it doesn't matter what we assume. The math will work out and get us the correct answer. Up at C, for our thin link, BC, we should have one force that goes along the member. That member looks like it's going horizontal, so we're going to assume that it is. So I'll just put in one force straight to the side, coming from B to C or C over to B. Let's call that CX. 2 feet down from C, I'm going to have a 300-pound force. So I need to get that in here. 2 feet down, 300 pounds, and it's going to the right. 300 pounds. And then from there, it's 3 feet to get down to point A. Then we can turn and start going over to the right. 2 feet in, 2 feet. I get my couple moment. It's clockwise, 750 pound-feet. 750 pound-feet. And then finally, 2 feet to the right from there, we have this 600-pound force. It's inclined down at a 60-degree angle. So 2 feet gets us to here. I have a force right here, 600 pounds. And my angle on this is 60 degrees. That should be my whole free body diagram. I have my unknowns in here, AX, AY, CX. 3 unknowns. I have 3 equilibrium equations I can work with. I can find all of these. So let's go ahead and go for it. We have our free body diagram. We'll come over on the right side and just apply equilibrium. So equilibrium. equilibrium in here. We got our free body diagram. That should be our first bit. Now equilibrium. So I would start this and say, is there any equation I could use where I would have just one unknown? I could sum moments at a couple places and make that happen. If I sum moments at A, I get rid of AX, AY, because they both pass through A here. That would be one place. I could find CX from that. I could actually sum moments up here at C. I would get rid of CX, and AY's line of action passes through there as well. So I get rid of CX and AY. I could find AX. Or I could sum forces in the Y. I only have AY as an unknown in here. Really, what I don't want to do is don't do some of the forces in the X first. I have two unknowns in the X. If we can avoid making two unknowns and not being able to solve it out, we definitely should. Let's do one equation, one unknown, if at all possible. So let's start by summing forces in the Y direction. If I sum my forces in the Y, I'm going to have, well, at A, I have AY. I assumed it went up, so it's positive. AY. I have my 600 pounds coming down. I want just its Y component, so minus 600 sine 60. And that's it. That's everything in the Y direction. I can set this equal to 0. When we're doing our equilibrium problems, make your entire equation. Even though this would be really easy just to start out and say AY is 600 sine 60, get your equation set up correct. Get that full equation. What am I summing up? It's equal to 0, and then solve it out. It will set you up to be more successful in the long run if you take the time to document your work well. Your professor's going to be happier with you if you have nicely laid out equations. Don't cut corners in engineering. But I can solve this for AY then. I'm going to get that my force AY is equal to 519.6 pounds. That's my magnitude right here. When I solve this equation out, it gets me a positive number. What that's telling me is in my free body diagram, I guessed the right direction. So in my answer, I'm going to include a direction arrow in here. It's going up. And we will always report our answers here, getting magnitude and use an arrow for direction. Always show as a positive, get the correct direction on it. That's one of my unknowns. I still have two unknowns in the X direction, CX and AX, so I still don't really want to come in and sum forces in the X. Why don't I sum moments at A? So say with positive, going counterclockwise, summing up my moments about point A. Again, I can eliminate AX and AY from this. Let's start up at CX. CX pulling to the left will cause a counterclockwise rotation about A, so it should show up in here as a positive moment. It's 3 plus 2, 5 feet away, so 5 CX. My 300 pounds will cause a clockwise rotation about A, so I'm going to subtract it off. Minus my force is 300, and my distance for this should be 3 feet. The Y distance from the force down to A, 3. We already said we don't include AX and AY. We will include this couple moment. It's going clockwise. That was a given piece for us. So just minus 750. It doesn't matter that that's located 2 feet in. This is already a moment. If I do pound feet times feet, pound feet squared really isn't a unit we even use. It's not a useful thing for us. This is already a moment. I don't multiply by distance on it. So I don't need to say times 2. We're good to go on there. Which means we can get to the 600 pound force. The X component of it will pass right through A, so the distance is 0, the Y distance for the X component, so it doesn't cause moment. I just need to get in the Y component's moment. That Y component going straight down here would cause a clockwise moment or rotation about A, so I'm going to need to subtract this one out. Minus my Fy, 600 sine 60, 600 sine 60 times an X distance from the force over to A, 2 plus 2, 4 feet, times 4. And that's everything that will cause moment about A. So I can set this equal to 0, equals 0. Again, we're making that full equilibrium equation. What are we summing up? Always stating what's our positive assumption in here. Always setting it equal to 0, and then solving for an unknown. If I solve for CX, I'm going to get that CX is 700 145.7 pounds. So I come in and do that, I'm getting a positive number out for CX here. That doesn't inherently mean that it's acting in the positive direction. All that's telling us is we assume the correct direction in our free body diagram. I assumed it was going to the left. Our equation worked out to get me confirmation on that. So I can put in a arrow to the left. And that would be our second answer for our problem. Finally, I'm down to just AX as an unknown. And again, there's multiple ways we could solve these out. I could sum moments twice. I could do, so I mentioned at the beginning, I could still sum moments at C and find AX. Or I could come in, and I think it'd be a little bit easier, I could just sum forces in the X, and I get there as well. So, taking the easy approach, because that's going to set me up to be more successful. More successful means I'm not making mistakes. I'm a better engineer then. So take the easy approach. It's not being lazy, it's being a good engineer. But summing forces in the X is going to get us, I have 300 going to the right. I have the X component of this 600 pound force plus 600 cosine 60 minus CX, because it's pointing to the left, so even though we found it was positive, we know the direction is in the negative X direction, so I'm subtracting it off. Minus 745.7. And then I assumed AX went to the left. Minus AX equals 0. If I solve that one for AX, I get that AX is negative 146 pounds. So what do? When we get that negative in there? I don't want to leave it negative. I'm going to come in and do two things. One, on my free body diagram, I make my students put in this dashed arrow in here. That way we're not changing our original assumption in here. We're letting people know, hey, when I started this problem, I guessed that it went to the left. As I did my math, I now know it's really going to the right. At this point, that doesn't end up playing into anything other than how we present our answer. But as we move forward, that's going to become really important for us, knowing which direction something's actually acting. So we're just trying to build good habits at this point. But then back here, we can say, rather than saying it's negative 146 to the left, we'll drop that negative and say it's to the right. Get the correct direction in here. AX is really a positive 146 pounds going to the right on here. If I had come in and originally assumed it was going to the right, my equation just would have changed here because I would have had a plus AX. When I solved it out, I would have gotten AX as a positive 146. We're getting to that same answer. We can assume any direction. The math will tell us based on if I have a positive or a negative, if I got the right assumption. If it comes out to be a positive, like we got here for AY and CX, then our free body diagrams, we guessed the right direction. If we get a negative, all it's saying is in our free body diagram, we guessed the wrong direction. Change that arrow around, put a dashed arrow in, report as a positive for the right direction. But hopefully this video was useful for us. We'll throw up a bunch of additional 2D rigid body equilibrium examples. These are, in my opinion, like key statics. When you ask people what do you cover in statics, they're probably going to say the sum of the forces in the X, Y are 0, and your sum of your moments is 0. Really, what we are doing here is the elevator pitch for what is statics. Everything sums up to 0. So we got to get this one down or we're not going to be successful in our course here. But hopefully this was useful for you. If it was, hit that like and subscribe. Stick around. Let's get you an A with JJ.